Welcome to our next video for Stat 420. In this chapter, we're going to be talking about variable selection and model selection. And so we're going to start with something we call quality criterion, or criteria plural, I guess. And those are the measures that we can use to help us determine what might be the best model for our analytical goals. And so just as kind of a overview here, what is a quality criterion? It's going to be a measure that helps us kind of measure our predictive power. But depending on the measure we use, it can also kind of guard against complexity as well. So when we think about choosing a model, there's really two ideas in mind here. The first is gaining predictive power and having the lowest amount of residual error possible. However, depending on our goals, we might also care about guarding against complexity and valuing interpretability. So depending on the measure we use, we can kind of balance these two things. That there are measures that are much more focused on this and don't really care too much about this. But then there's other measures that we can use that will actually value this as well in case that's something that we really care about. And the reason we care about the second part is because we might favor a model that's a little bit easier to interpret and favors more of this simple relationship. Maybe it uses fewer parameters, so it's a little bit easier to use. Maybe it's a little bit less expensive or difficult to use. And we also might just favor interpretability in terms of understanding how variables relate to one another, as opposed to how much predictive power can we get. Because maybe we can add 4 or 5 or 10 more terms to a model and get a little bit more predictive accuracy, but maybe it's not really worth it in terms of the model's use and how difficult it is to use at that point and collect all of that additional predictor information to actually use that model. So quality criterion are going to be measures that balance these different things in different ways. A couple of them we've seen before, but a couple of them are going to be new for this section as well. So we've talked about R squared, and R squared is just going to measure how much variance is being explained in our response by this particular model, by the predictors that we're using. And so R squared, though, is not a very good measure for model comparison. And that's because R squared can only go up as we add more terms to a model. However, R squared is not going to tell us when we're actually overfitting our sample of data. So overfitting happens if we have some data and we start adding complexity to actually kind of go after the individual data points as opposed to actually modeling the general relationship that we see. And so that happens a lot when we have not a whole lot of observations, but we have a lot of parameters that we're adding in, because if we have about as many parameters as we do observations, then theoretically I can just create a function that actually includes every observation exactly, and I have no residual error. But then I get to some new data and I try to put that model on top, and I see that it has nothing to do with the data and the relationship that actually exists. I was just modeling the noise at that point. So for that reason, R squared is only good as a descriptive measure of how much variability we're explaining on this particular sample of data, but doesn't actually do a good job of telling us which model is best and which model we should use for additional data as well. So that's where adjusted R squared often comes in, is that adjusted R squared is going to actually adjust for how much correlation we're likely explaining by random chance by adding an additional predictor. So every time we add a predictor, we're probably explaining a little bit of random chance correlation. Because I have more information, I can try to fit this sample of data a little bit better. But adjusted R squared is actually going to go down if the amount of correlation, if the amount of variance in the response being explained is actually less than I would expect by random chance when I add another parameter like that. So adjusted R squared is only going to go up if I'm actually beating random chance with that additional parameter being added. So in that sense, adjusted R squared can help us find an appropriately fitting model if we see that adjusted R squared goes up. That said, simply beating random chance is not a very high bar to get over. So adjusted R-squared is still going to favor fairly complex models because I can find terms that are going to beat random chance that maybe aren't actually, correlated. Because simply beating random chance doesn't necessarily mean I'm highly confident it's adding anything to my model, just that I think it's more likely than not that it is. So for that reason, adjusted R-squared is not a particularly choosy measure for choosing a model, but it's certainly helpful. It's also a very easy thing to calculate, especially if I have like my summary of my model, and adjusted R-squared is going to come out with that. So it's kind of a nice quick hand reference to see if the model that I'm looking at, the predictor that I added, is at least doing better than random chance. But typically we're going to want to use either cross-validation or a measure like AIC or BIC when we're doing some serious model selection. So cross-validation we have actually seen before just on what's called one-fold cross-validation, where we split our data into training data and test data. We fit our model on the training data, and then we see how well it's predicting the test data using that particular model. So we'll talk more about cross-validation where we go beyond just one fold, but actually consider what's called leave one out cross-validation, and why that's a little bit more robust for checking against overfitting and seeing which model really has a stronger predictive power across new data. But for now, just know that cross-validation is one strategy that I could use for model selection to see which model really has a stronger predictive power, even on a new set of data not used in the fit. AIC and BIC serve similar purposes. They just go about that a little bit differently. They do measure how much residual error I have left over, but then they also are going to subtract for having more parameters. So the goal here is to have the least amount of residual error possible. And if that's all they did, they'd really be equivalent to R-squared in that sense. They're just finding which model has the least amount of residual error. But AIC and BIC both add a penalty for every predictor or every parameter that you add to that model. AIC has a smaller penalty than BIC, which means that BIC generally favors a simpler model than AIC. But we'll talk more about that later as well in this video, as long as you just kind of had this overview here of these are the different methods that we're going to be talking about. All right, so just a reminder about overfitting. I mentioned that already. But here's an example where I have a sample of data, and this blue line right here represents a rather simple fit. It's just a quadratic fit that's kind of looking at what seems to be the overall signal. But I can keep adding parameters. I can keep adding higher order polynomials and trying to fit this data more exactly. And what happens is I end up, if I do an 8th degree polynomial, I end up with this orange line, which is actually fitting this particular sample of data really well. The issue is that this orange line is kind of ignoring the fact that there is going to be some noise in this data, and I shouldn't expect to find a model that fits the data exactly, but that should fit the overall signal between these two variables. So it turns out that this orange line, even though it has the lower RMSE, it has the lower amount of residual error in its predictions and actual data points here, is really not a good model, because if I got some new data, I'm going to have different noise, and I'm instead going to have something like, maybe something kind of like this. And if my orange model looks something like, this, it doesn't really make a lot of sense, because that model was fitting that particular sample of data and not the overall signal like the other model was. So this is why overfitting is kind of a concern, and why only looking at my residual error all by itself as the only measure is really not a good way to choose a best fitting model.